This is reserve problem number 11 in chapter 6. We will use the correlation and regression tool packs from Excel. Dura-Rob makes rubber door sealings accessories for industrial uses. The company wants to test how closely the hardness of their door sealing products is how the hardness is correlated with temperature. It is known that the higher the temperature, the lower the hardness, beginning at around 35 degrees centigrade or 95 degrees Fahrenheit and up. So what we must do is use this data set right here, and we will use the regression and correlation tool pack, and we should interpret the results, and we should also see if the oven is increased to 60 degrees, what would be the predicted hardness. So, because we're predicting hardness right here, wonder why my pen isn't, there we go. Because we are predicting hardness, so in regression, always the predicted variable is going to be the dependent variable. So in this case, hardness is what we're predicting, and this is going to be the y variable or dependent variable, and temperature is going to be the x or independent variable. All right. So with that said, let's go ahead and use the data analysis tool pack, and we will use the correlation tool pack, and it says what is the range. Notice I'm including the headings, temperature and hardness. The data is in column, so I'm going to keep that as checked off. And we do have the heading captions, so I'm going to put labels. I'm going to check that off. And my output, I can put it in this cell right here, E2. And with that, I'm going to say OK. And we get this output right here. Of course, the temperature with itself and hardness with itself have a perfect positive correlation. But we have a very high negative correlation between temperature and hardness. So as temperature rises, hardness decreases is what this is essentially saying. Just as a recap about what correlation coefficient is, it's an index, R, which is called correlation, Pearson's correlation coefficient, is an index. It's unitless. At 0, there is no linear relationship between the two variables. +1 means perfect positive correlation or association between the two variables, and oops, it's because I have this positive here and I need to put that. Oops. Oh, I can't. There we go. +1.0. Okay, and a negative 1.0 means perfect negative relationship or correlation between the two variables. Okay, so in this case we have a negative and very associated, high association between the two variables. Just so that you know the absolute value of the correlation coefficient, anywhere from 0 to about 0.3, 0.35 means low correlation. Then from about 0.35 to about 0.75 is considered moderate correlation. And from about 0.75 to 0.9599 is high correlation. And of course, +1 and -1 are perfect, are represented by the perfect being the association. Okay, so now we want to perform a regression analysis. So scroll down to regression. And it says, what is the Y range? In this case, as we determined, hardness is the Y. X range is the temperature. I do have labels, so I do want to make sure that I check that off. And I'm going to put the output, let's put it over here. And that's fine. I don't need any of the other results. So here's my output for this analysis. Let's go ahead and interpret this quick. Again, going to my pens. We have the multiple R, this right here. This is the correlation coefficient. But notice that this is correlation coefficient. I cannot type. Can you tell? Correlation coefficient. Notice here, this is very important, that the sign, the true sign, is negative. The two variables are negatively correlated, but regression output does not put the sign. That's because you need to get that sign from oops, not there, from you need to get the sign from the slope. And over here you can see that the slope is negative, and so we know that this right here has to be a negative 0.93. So if you don't compute the correlation coefficient on your own, and if you just rely on the regression output, you need to be careful to look at the sign for the slope. Another way, of course, that you can compute the correlation coefficient is just by the Correl function. So you can say equals correlation and then array 1, and in this case it doesn't matter which one you put first and which one you put second. Then separated by a comma, array 2, oops, not there. Array 2 is right here. And if you press enter, you get the negative 0.94. All right. The next item is this one. This is R squared, really, which is the negative 0.93858 squared. This we call the coefficient of determination, and it can be interpreted as the percentage of variability in y, in the dependent variable, given x. So what percentage of variability in y is is associated with or is accounted for by the value of x. And you can see that this is fairly high in this case. We have an 88% of the variation or variability in hardness that is associated with or explained or accounted for by the temperature that is used in the process. So that's a highly correlated and highly associated relationship. This third one right here is adjusted R-squared, and that's generally used for multiple regression situations, applications. Of course, we had 15 observations, so that's what that is. That standard error is essentially the standard deviation for the regression line, if you will. Okay, our equation, therefore, our regression equation is y is equal to, or predicted y, or predicted hardness, is equal to 127.35, which is the slope, which is the intercept for the line, minus, or we can say plus, and negative 0.694 times the temperature. So that's our predictive model. The question was in the problem, what if the temperature is 60? So in this case, we would say hardness at 60 or 4 when temperature is set to be 60, or at temperature of 60 equals. And over here we can use our equation, which is the intercept. I'm going to erase this right here. I'm sorry. Okay. So we have equals our intercept plus our slope for the regression line times 60, which is our measure of independent variable. And so the hardness will be 85 when the temperature is set at 60. We can create actually I want to use the scatter diagram, and you can see that hardness and temperature are negatively correlated in this situation. Okay, so I hope you found this helpful. I want to know. Oh, and about the significance level of the test. Notice that our significance F is this is our essentially our p-value for the F test. There we go. This number right here you can see is the same as this number right here, and it always will be the case when you are working with a simple regression where you have only one x variable. And this essentially is, notice how high our calculated f value is. So essentially we're saying that there is high evidence, statistically significant evidence, that this model is in fact valid, and the hypothesis test that is conducted here, that Excel conducts, is this. H naught says that beta, or the slope for the test, is equal to 0, meaning there is no relationship between the two variables. An alternative hypothesis is that beta, or the slope for the test, is not equal to 0. So we just proved here from the Excel test that we can reject the null, and therefore the slope is not equal to 0, and the slope is negative, and that there is a negative relationship between these two variables. I hope you found this helpful.